Hi, everyone, and thanks for joining me today for episode 855 of People Behind the Science. I'm your host, Dr. Marie McNeely, and today we're revisiting our interview with our guest, Dr. David Sedlak. Listeners, David is working to create technologies that will allow future generations to have access to adequate amounts of clean, safe water. He and his team are studying everything from the mechanisms through which chemicals are degraded in advanced water treatment plants to the ways in which nature-based treatment systems can be integrated into water treatment. And in our conversation, David shared some fantastic stories about his life and his research. So I hope you enjoy this episode of People Behind the Science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to the People Behind the Science podcast. Today, we are delighted to be joined by our guest scientist, Dr. David Sedlak. So, David, welcome to our show today. How are you?
I'm doing very well. Thank you.
Well, thank you so much for sharing some of your time today. I'm excited to introduce you to our listeners. So let me first start by telling them a little bit about who you are and what you do. So listeners, David is the Plato Malozemoff Professor in the Department of Civil and Environmental Engineering, co-director of the Berkeley Water Center, Deputy Director of the National Science Foundation Engineering Research Center for Reinventing the nation's urban water infrastructure, and also Director of the Institute for Environmental Science and Engineering at the University of California, Berkeley. In addition, David is author of the book Water 4.0, The Past, Present, and Future of the World's Most Vital Resource. David earned his bachelor's degree in environmental science from Cornell University, and after college he worked as a staff scientist at Environ Corporation in Princeton, New Jersey. David then attended graduate school at the University of Wisconsin-Madison, where he was awarded his Ph.D. in water chemistry. And prior to joining the faculty at UC Berkeley, David conducted postdoctoral research at the Swiss Federal Institute for Environmental Science and Technology in Switzerland. Throughout his career, David has received numerous awards and honors, including a National Science Foundation Career Development Award, the Paul L. Busch Award for Innovation in Applied Water Quality Research, a Fulbright Senior Scholar Award, a Fulbright Alumni Initiative Award, the U.S. National Academy of Engineering Gilbreth Lecture Award, and the Athalie, Richardson, Irvine, Clarke Prize for Excellence in Water Research. He has also been named an elected member of the U.S. National Academy of Engineering, as well as a Rydell Distinguished Visiting Professor at Gustavus Adolphus College and the Francqui Foundation Chair of Ghent University. In our interview, David, we are looking forward to learning more about your research, but we'd also like to know more about you. So can you start by telling us what you like to do when you're not doing science?
When I'm not doing science, I like to be out running long distances, and living where I do in Berkeley, that usually involves running on trails that go through the hills around the Berkeley.
Excellent. So are you like a marathon runner, or do you compete?
Once a year, I try to run a trails marathon, and that's only to give me an excuse to spend the summer training and getting out of house chores while I'm training.
Soaking up the sunshine. I like it.
Indeed.
Very cool. Well, it sounds like a wonderful way to expand your mind, get away from the science a little bit, get out there, get active. But I'd love to talk about your science as well. So how do you describe your work, David, to people who aren't familiar with your specific research area or maybe aren't a scientist?
Well, in some ways, I'm not a scientist at all. I'm an engineer. And the kind of engineering I like to do is to create the technologies that will allow future generations to have access to adequate quantities of clean, safe water.
Excellent. I think that's something that's been at the top of mind for a lot of people these days as we're starting to experience water shortages and some water quality issues. So I think this is a phenomenal research topic, and I'm looking forward to learning more as we go through our interview today. But I think as a scientist, there are a lot of ups and downs, and I think it can be helpful to have bits of motivation and inspiration to help you out in those troughs. So David, do you have a favorite quote or a saying or just a force that really motivates you?
I do have a favorite saying or quote for motivating myself. I don't know if it was said by someone, but it's something that I've developed over the years as I think about my research. And it's this: if it were easy and obvious, someone would have done it already. So one of the really most important problems for a researcher is to figure out the right questions to ask. And I think that's where a lot of the creativity comes into the whole process of conducting research. So the human inclination when addressing a problem is to look for the simple and easy things to do. But that runs into conflict with actual research, because if you're going to do cutting edge or research on the forefront, you often have to go out in new directions that people haven't yet taken. And that is the place where the obvious things, you're probably just going to make incremental contributions. And the easy things, well, once in a while you're fortunate and the easy things work on the first try. But my experience is that the good ideas usually take a bit of perseverance to get through.
Definitely. I think you got to stretch a little. You got to reach for some of those tough questions in your work. And I'm curious to hear a little bit about some of the people who might have made this possible for you, David. When you think back over the course of your career or your life, are there particular people who may be scientists or just role models or inspirational figures that you've looked up to?
The first person who inspired me to think seriously about a career in science was my high school chemistry teacher, a woman named Lillian Murad. And what was so motivational about her to me was that she saw the science of chemistry as a multidisciplinary effort that not only had connections to biology and physics, which are obvious, but to history and to art and to even politics. And I think that broader view of how a scientist is not limited by just the rigid guardrails of the discipline made me recognize that I could pursue a passion for science and still not shut off the other things in life that I found so fascinating.
Oh, very cool. So can you talk a little bit then about where your scientific interests began? You mentioned this high school chemistry teacher was key to getting you inspired. Were you interested in science before then or interested in engineering?
I was interested in the environment. So I grew up in a town called Oyster Bay. It's located east of New York, Long Island. And I guess one of the best parts about living in a place like this is that you're obviously close to the water. So as a kid, I spent a lot of my time along the water. And as I got older, I started to learn about and see and experience pollution. So to me, that question of how we can live in harmony with the natural environment was really what motivated me. And when I saw that science could be part of the way in which we could achieve that, that's what attracted me to study it more. So when I went off to university, my first major was natural resources. So I thought maybe I wanted to study forestry or fisheries or lake management or something like this. And very quickly I saw that it wasn't so much the management-oriented sciences, but the sciences that involved solving environmental problems at a larger scale that were so attractive to me.
Certainly. So were you able to get involved in research during your undergraduate days there at Cornell?
I got involved in research right away. I think in my second year, because I qualified for work study, I worked in a laboratory, and that made me see that the skills that I was learning in my courses actually applied to answering scientific questions. And by the summer of my second year, I was already working for one of my professors doing summer research. And that just started a process that one thing led to another. And I was always doing some kind of research as an undergraduate.
Certainly. Then what prompted you to make that big decision to go to graduate school?
When I finished my undergraduate, I have to admit, I was pretty burned out. If you're busy taking the hard technical electives required to major in science and working in a laboratory and working to earn some money on the side and having some semblance of a social life, you're pretty tired by the fourth year of your undergraduate.
Mm-hmm.
So I didn't want to go straight to graduate school. I wanted to get a job. And after I graduated, I worked for a couple of years for an engineering consulting company that was involved in cleaning up hazardous waste sites in the New York City area. And that experience of working with real polluted sites and communities that were facing the impacts of pollution was inspiring. But I also saw how little I actually knew about how to solve the problems. And in that job, I was working with people who had master's degrees and Ph.D s. So it was pretty obvious to me that the next step was to go to graduate school. And these problems that I was dealing with during my time in the work world generally revolved around chemicals that were contaminating the environment. And at that time, a lot of the effort that people were spending in cleaning up chemicals had to do with characterizing their movement and the way in which they affected human health. And very little of it was focused on finding ways to destroy them. So that became my passion. I was really interested in developing technologies that could destroy chemicals that were contaminating soil and groundwater. So that's what I went to graduate school to study.
Certainly. So David, can you talk us through then, what was your experience like there at the University of Wisconsin-Madison when you were doing your PhD?
Well, first of all, Madison is a wonderful place to live and to be a student. One of the greatest things about living and working as a graduate student in Madison is, first of all, it's a college town, so you're surrounded by fellow students. And second of all, there are very few things that you could want to do there that cost a lot of money, which is something that's important when you're a graduate student and living on a graduate student stipend.
Right.
But my experience in Wisconsin was wonderful because my research advisor gave me a lot of freedom to explore the kinds of problems that I was passionate about.
Very cool. And then afterwards, you took a big leap with your postdoc. You actually worked at the Swiss Federal Institute for Environment, Science, and Technology in Switzerland. So was this a difficult transition for you?
Well, as an undergraduate, when my fellow students were going off for a semester abroad, I could never fit it into my schedule. But I knew that someday I wanted to have an experience living in another country. And it turned out that in my field, some of the best researchers in the world are based at an institute just outside of Zurich, Switzerland. So I, believe it or not, wrote a letter to one of the professors there and asked if he had any positions available to him. And to my surprise, he wrote back and said that he did and that he would welcome me there as a postdoc. And that to me was a real eye-opening experience because back in the 1990s, it was hard to really learn about a place you'd never been before. You could only really research it in books or watch movies about it or talk to people who've been there. I know that's hard for people living in the post-internet age to recognize.
Wrap our minds around, yeah.
But to me, it seemed like the end of the world and was something to adjust to. But it was a relatively simple adjustment because at the institute I worked in, just about all of the day-to-day scientific business happened in English. And they had a long history of welcoming people from all around the world. So I felt like a kid in a candy store surrounded by some of the best researchers in the world with some of the finest equipment and many of the cutting edge ideas being discussed every day.
Oh, that's awesome. So David, can you tell us then how you found your way to Berkeley for a faculty position?
When you're a graduate student or postdoc and you start applying for jobs, at least in my case, I was not very picky about having to land in a specific part of the country or the specific university. I just knew I wanted to be at a university where I could conduct research and teach and interact with students. So when the position at Berkeley came up, like many of the other positions that I was applying for at the time, I just applied for the job. And it was a good fit for what Berkeley was looking for at the moment. So I found myself here, fresh out of my postdoc.
Oh, I love that. And I love that you really hinted at this fact that it was sort of being at the right place, applying at the right time, and all the pieces falling into place, because I think a lot of students worry about having everything planned out from the get-go, and that's just not how it works most of the time.
Indeed.
Well, it's been great to chat about your career path and learn about how you got to where you are today now there at Berkeley, but I'd love to talk about some of your research projects. So, David, is there one in particular that you are working on right now that is just the most exciting that you want to share with us?
It's really hard to just choose one topic that's really interesting. But if I have to come up with one project that really has my passion at the moment, it's a project that we're working on that we call the horizontal or living levee. Mm-hmm. The idea behind this project is we create a natural treatment system that is a subsurface wetland, and we build it adjacent to a flood control levee. So, for example, in San Francisco Bay, we have levees that ring the bay to protect communities from storms and in the future from sea level rise. And by putting a wetland between the levee and the bay, we're able to protect the levee from the forces of a storm surge when a storm comes. But we can also use this levee as a natural treatment system. So what we do is we take polluted water, and in this case, the first type of polluted water that we've studied is the waste from sewage treatment plants. And we put it through the subsurface of the wetland, And the microbes that live in that subsurface environment break down many of the chemicals and produce clean water as it passes through. And in the process, the plants that are growing on the surface of the levee extend their roots down into the water, and they take up the water and grow. And by working with a local environmental group called Save the Bay, we've managed to plant it with native plants that are creating a habitat which is unusual in the San Francisco Bay. It's a terrestrial habitat, which is very attractive to many of the native species. So at this point, we've built a system that's a small, maybe 500 or so meters by 50 meters wide. But the idea in the long term is to replicate this type of levee all around the bay and use it to create protection against sea level rise.
Oh, that's so cool. I have to ask, though, are the wastewaters, I know you mentioned in this case, you're looking at the output from sewage treatment plants, are they detrimental to the plants you're trying to grow there?
Actually, the plants love them.
Really?
Because they're really rich in nutrients. So it's almost like applying a nutrient solution to the plants. And that's a great part about it, because if we don't pass it through the wetland, those same nutrients go out in the bay and cause algal blooms. So scientists studying the bay are quite worried about the effects of nutrients going out to the bay. And this system that we built offers a low-cost, nature-based approach for protecting the bay from nutrient pollution coming from the sewage treatment plants.
Oh, that's so cool. So, David, if this works well in the Bay Area, do you have your eyes on other places you think might be good applications for it?
Yes, we've started to think about other places where we might apply this. And one of the things that we've done since starting it with the wastewater is we've started thinking about the treatment of the wastes that are produced during water recycling projects. And those wastes are produced by the process of reverse osmosis. So if you want to turn sewage effluent into drinking water, one of the tools that you use is reverse osmosis. It's the same technology that's used to turn seawater into drinking water. If you do it with sewage effluent, it uses a lot less energy because the treated sewage has a lower salt level. But when we use this technology of reverse osmosis to recycle wastewater, we're left with this concentrated salt and nutrient and chemical solution that we have to dispose of. So we found that the horizontal levees are also good at removing contaminants or purifying this reverse osmosis concentrate. So now we're looking at other parts of the world where people are using this reverse osmosis process for drinking water production. And one of the sites that I'm quite interested in is located along the coast of Belgium, where they've been recycling water with this process, but they've been sending the concentrate directly to the ocean.
Gotcha. That is phenomenal. Well, you've described some really interesting projects here, but I imagine you encounter some challenges as you try to solve some of these big issues that we're facing in terms of water availability, water quality. And I love talking about the challenges, the failures, because I think these are the hidden stories that our listeners out there don't often get to hear. So when you think back on your own research, maybe what's happening now or some earlier parts of your career, David, what are some of the biggest challenges you've faced or failures that you've had?
No project worth doing is without its initial failures. And I normally just shrug off failures and think of them as part of the necessary steps to getting somewhere. So I rarely even slow down or get put off by failures. But there have been projects that we've tried to do where the process of failure has lasted a lot longer than we would have liked. And I can think of one that happened very early in my career, where we were trying to measure concentrations of a synthetic estrogen. This is ethinyl estradiol, the active ingredient in birth control pills. And we're trying to measure it at very low concentrations. And the technique that we were using to measure it worked quite well in the laboratory, and it worked well when the water was pretty clean. But when we went out and actually tried to apply it in the field, we got data that didn't make a lot of sense. And I remember one of my graduate students spending 3 or 4 months in the field working day and night to collect and process samples. And we looked at the data and we just said, this really isn't useful at all. And that was around the time when I was thinking about my tenure case going in and the university making a decision whether they wanted to keep me around, and having this year or two of research and all of the funding that we had to support it just kind of go up in smoke in front of our eyes.
Oh, no.
So we just did what you always have to do in this field. You go back to the drawing board, you find a way to tweak and improve the method. And we spent the next year back in the field, repeating the same experiments that didn't work from the year before, and ultimately managed to get the project done. But I'd have to admit that the year-long delay as we tried to fix the problems that we encountered were a stressful time, both for the graduate student and for myself.
Absolutely. So did you ultimately figure out what it was that made things not work out that first year?
Oh, we certainly did. I mean, it turned out that you're basically trying to measure a concentration of a chemical in the part per trillion levels when you have all these other chemicals and organic matter there at the part per million level. So you're really trying to pull a needle out of literally a million pieces of hay. And to do that, you have to clean up the sample and purify the sample. And we thought we had the sample pretreatment and purification methods nailed down. But when we went out to the actual field site, it was just a lot dirtier than what we'd expected. So we went back and redoubled our efforts and actually end up finding some more rigorous but time-consuming pretreatment methods that made it possible to measure the compounds.
David, I have to ask, how did you keep it together in that whole year that you had to wait to start the field trials again? And maybe how did you keep your graduate student calm and assure them everything was going to be okay?
Well, I was very fortunate that this particular graduate student was one of the calmest people that I've ever met in my life. And I think he would have been happy to have another year in graduate school because he had plenty of other hobbies to keep him busy. In my own case, I think that I had already been involved in enough science where I realized that, like I said before, anything worth doing generally isn't easy and it isn't obvious. So I believed in the project and I believed that we would be able to overcome the barrier. So I viewed it more as a puzzle to be solved than a mountain to be climbed. So I found it exciting and stimulating to try to get around this challenge as opposed to just a sense of dread. And maybe I'd be singing a different tune if we never managed to find a way to solve that problem. But my experience is that when you find technological or research challenges that are insurmountable at the moment, you rethink the question a little bit and you try to figure out which questions you are able to answer with the tools that you have. And sometimes answering those turns out to be just as significant as the problem you started out wanting to answer.
Definitely. And I really appreciate what you pointed out here in terms of your perspective, because I think oftentimes it's easy to fall into that this is a huge insurmountable challenge I'm facing when you really could reframe it as, well, this is an interesting puzzle I'm trying to solve. So that's very helpful. And this ultimately resulted in a success, David. And we love talking about the success stories of scientists on our show as well. So do you have another success story, whether it was a big win or just a small victory that you found particularly meaningful that you want to tell us about today?
I'll tell you about a recent win that I'm really excited about. And again, it came from a source of frustration with something that wasn't working. About 8 years ago, a postdoc of mine was doing a series of experiments where we were trying to break down a very simple organic chemical, benzene. We were breaking down benzene by using an oxidant that produced something called a hydroxyl radical. And in all of the textbooks, you see that this is a very simple reaction, which just has one product. And we decided we'd try to run an experiment where we watch the disappearance of benzene and the formation of the product, which is a compound called phenol. And what we found is that we only could account for about half of the benzene that was lost. So I said to the postdoc, well, we better go back to the lab and repeat the experiment and make sure we're just not losing some of this stuff, because benzene is a pretty volatile chemical that can leave the system just through the air. And to make a long story short, it started a research project that has taken about 7 years to really solve.
Oh, wow.
And what we found out is that there are multiple reactions happening in that initial oxidation state of benzene. And the products of the reaction are a lot more complex and in some cases much more toxic than the phenol that we thought was the only product initially. So that led to a series of papers that have come out within the past year where we've shown that there's this previously unrecognized or at least under-recognized pathway when you're treating simple chemicals like benzene, and that you need to pay attention and measure them and try to identify ways to minimize their formation. And I think that what I found so rewarding about working on that problem was the fact that when our team didn't take the easy answer of just saying, well, we can't explain half of it, but we want to move on to other things. Rather, we took the approach of saying, we want to try to understand what we're missing, and we're going to use all the tools that we can to try to identify it. What was most gratifying was we discovered something that no one had seen before. And that really makes me feel very optimistic about the approach of doing science and the need to be careful and thorough in what we do.
Certainly. And you mentioned in this case, you were identifying products that were actually more toxic than what you had thought was being produced. And I think this is fascinating. But does it also give you a hint of concern when you see these results coming out if it has applications in the environment and water?
Right. Well, the first thing that we did when we found these toxic products being formed is we started asking questions about whether they would break down after they're formed, either by the presence of the oxidant or if the water samples encountered microbes. And so what we learned was that if after these compounds are formed, we subject the water to biofiltration, that is, if you push past the water through sand that has bacteria living on it, it turns out that many of these chemicals break down readily. So we kind of identified a wrinkle in this, is that you can't or shouldn't perhaps just employ an oxidant without this biofiltration step afterwards. But it definitely raises questions about anything that we try to do in the water treatment area, that the fact that there are often unintended consequences of trying to clean up pollution is really a theme that we see over and over again in our research.
Absolutely. Well, congratulations on this exciting research success. And we've talked about some different aspects of your life and your career. And one of the things we haven't touched on yet is what you like to read. And I mentioned in our introduction, David, that you are an author yourself. So I want to make sure we talk about your book from now several years ago, but also if you have any book recommendations you'd like to pass on for us today.
I do have a reading recommendation that was very inspiring to me this year, and it was a book called Factfulness by Hans Rosling and his daughters, Anna and Ola, that just came out in the past year. So Factfulness is a book about the world and why things are better than you might think they are. And I think that this is a really important topic in these days when we're so concerned about things like climate change and income inequality around the world. And what I really love about this book is that it shows with scientific data the way in which global development is changing the world and lifting people out of poverty and improving public health. And it's not to say that there aren't things we should work on, but I think that there's a tendency, especially when you study the environment, to forget about the victories that happen along the way. So there's a lot that we have to try to overcome and a lot of problems that need fixing. But once in a while, we should step back and think about the things that we have succeeded in and use them as inspiration for the next mountains that we have to climb.
Absolutely. This sounds like an awesome book. We will add it to our website for our listeners to find there. And I do want to make sure we add your book, Water 4.0, as well. So, David, can you give us a little teaser about what this book is about?
Sure. So I wrote Water 4.0 about 5 or 6 years ago to describe the history that created the systems that provide us with water and the challenges that our modern water systems are facing. So it's a book with very little actual detailed science in it. It really talks about the technologies that we've developed, the institutions that have formed around our water systems, and the ways in which we're facing significant challenges to providing safe and clean water, but also the ways in which the innovators and early adopters of technologies are solving those problems.
Certainly. So in writing this book, I imagine you had to do a bit of research into the technologies, the companies. Did you ever get tempted by this entrepreneurial world or this industry world?
I've never been tempted to become an entrepreneur or start a business because I view the research that I do as an entrepreneurial business of its own. And I love this business that I'm in and see no reason to jump into one that's more commercial.
Gotcha. Well, great to hear about some of these phenomenal books. We will make sure, as I mentioned, to put them on our website. And throughout our conversation, David, we've touched on some of the places that you've been for your science, but I'd love to dig in a little deeper. I know as a scientist, you get many opportunities to travel, whether it's for field research or whether it is to meet with collaborators, to go to conferences. So do you have a favorite place that your science has taken you?
I have indeed traveled to lots of places to conduct research. I know many researchers around the world, and I feel in many ways like I'm part of a global family. But my favorite place where my research has taken me is to Berkeley, California, and the University of California at Berkeley.
Aww.
I'm sorry. I'm going to gush blue and gold because the place where I am, in my opinion, is a little bit unique. It's far enough away from Silicon Valley that we don't have this starstruck idea that technology is going to save us from everything. But it's close enough to this long-standing history of Berkeley in trying to solve the world's problems that it's the place where I feel most stimulated and most closely links to the way I view the world.
Certainly. And you've been at Berkeley now for a number of years. What was it like for you first stepping foot on this campus when you got that new faculty position?
Stepping onto the Berkeley campus was a bit intimidating, to say the least. You know that there have been many famous researchers over the years who've established whole disciplines at this place. So coming to Berkeley really made me question whether I was an imposter or not.
I think many people have struggled with this imposter syndrome, particularly in those early stages of their career. So how did you overcome it?
The imposter syndrome is something that just never goes away. I think many of us have it as students and then as postdocs and, yes, assistant professors and associate professors and full professors, because every time you're thrown into a new situation where you haven't established yourself yet, there's a part of your brain that wonders if you're really what they think you are. So I don't know that I've ever conquered the imposter syndrome. I've just become more familiar with it. And I use that fear of people discovering I don't belong to focus my energy to making sure that I don't actually find myself in that situation in reality.
I like it. And you mentioned that Berkeley is a special place. So can you tell us, David, what are some of your favorite spots either on campus or in the area that you like to go to?
Well, if you come to visit Berkeley, you have to walk through the center of the campus to the Campanile or clock tower. And I suggest you take the stairs of the elevator all the way to the top and have a look around at 360 degrees and listen to the bell towers. After you've done with that, I would suggest taking a walk around the campus and randomly find yourself in different lecture halls, because the real treat of being at this university is there's something interesting happening in every single building.
I like it. Well, thank you for talking about one of these places that's been so meaningful for you in your life and your career. And we touched throughout our conversation on some of the projects that you've worked with students, with colleagues. And I think oftentimes in science, the people are what really make the career special. And I know as a scientist who does quite a bit of field research, I imagine you have some funny stories or unexpected happenings that have occurred to you during these projects. So do you have a story of one of these experiences you can share with us today?
I think the story from my field experiences that sticks out most in my mind is when I was a postdoc and was working on a project to collect cloud droplets. Now, you wouldn't think that someone who studies water would have much to do with all these atmospheric scientists, but the chemistry that happens in cloud droplets is actually quite fascinating because they get sunlight shining on them and they have trace amounts of metals and soil in them, and there's a whole variety of oxidation chemical reactions going on in cloud droplets. So they really are interesting models for treatments that you might use to purify water. So I got tied to a project in northern England when I was a postdoc where we were supposed to go out and collect cloud water samples. And I was very naive. I didn't have much experience collecting cloud water because it wasn't in my topic area. Mm-hmm. So I rented a van and I brought my equipment with me and I brought my field technician with me. And it turned out that all of the other groups had not vans, but they had recreational vehicles with electricity and heat and refrigerators and music and everything else. Ooh. And my technician and I were in this van that we couldn't run the engine because we were in the middle of this experiment and we didn't have any electricity. So we're in this cold, dark van and it was about 40 degrees and the wind was blowing at about 50 miles an hour. And we had to be there for like 36 hours at a time.
Oh, geez.
And there was a bit of a rebellion with the technician. And the technician happened to be my wife because I was the only person I could convince to come with me to England to collect cloud water samples. So at about 3:30 in the morning one night, she said, I'm leaving. I'm going to go into the van with the Germans because they have heat and they're drinking coffee. And I think they're playing music too.
Oh, wow.
So I said, you can't leave me here. We have another sample to collect in a half hour. So somehow I convinced her that if she just stuck it out for 3 more hours, we'd go and try to find some warmer blankets to help us get through the next night.
Mm-hmm.
But the two of us were pretty miserable during that field sampling. And I've never gone out cloud water sampling since.
Oh, that is hilarious. She was ready to defect to the RV camp. I don't think I blame her. So how do you sample cloud water?
You use something that looks a little like a tennis racket where the strings are only strung in one direction. So you take these nylon strands and you orient them in the direction of the wind, and then you turn on a fan that sucks air across these filaments, and it all collects on there and drips into a little bottle. So you can get about a few hundred milliliters of water every hour if you just run the fan and suck the cloud through there. But the trick of it is you have to go up on a mountain or a hill that's high enough that it's intercepting a cloud. So we've all kind of been places where you can see at the top of the hill, the cloud is set in. So that's the kind of place you want to go to collect your cloud water.
Gotcha. So we're not talking like low-lying fog. These are actual, like you're on a mountain on a high hill collecting actual clouds. That's so cool.
It was very cool in the van.
Right. For better or worse. Well, thank you for sharing one of these funny fieldwork stories, because I think it does show that science doesn't always go as expected. And I think it shows this side of science that people don't always realize when they think about people just always working in the lab. So we've talked about a lot of cool projects that you've been able to work on over the years. But David, I'm curious because I know oftentimes in science, you're bounded by different barriers, whether it's funding, staff, technology, feasibility, whatever the case may be. So if we took those barriers away and gave you everything you could dream of, what is the one question you would most want to answer, or the one problem you would most want to solve?
I would love to have the opportunity to develop a house where all of the water in the house flowed in a loop and was never lost. That is a fully water recycling house. So that's been a dream of mine for a while, but this fully water recycling house would not only purify the water, but it would produce different qualities of water for different uses within the house. For example, you could have the drinking water with the ion composition that tasted best to you, and the water that went out in the garden might have nutrients in it that could be used to water the plants, and the water that went to wash the clothes might not have the kinds of divalent cations that cause the soap not to foam perfectly. And I would want to develop something like this that was cheap and easy and could be used in communities where it was too challenging or expensive to run a conventional water supply. So imagine something like the International Space Station that was modular and inexpensive and could be run with a solar panel or a small amount of energy.
Oh, that is so cool. So what do you see then as the major barriers, or maybe some of the biggest challenges to getting there?
I think one of the barriers to taking these things which are imminently manageable now, but to making them inexpensive, that they would be accessible to people in low and middle income countries and in rural communities, is figuring out how to manufacture them inexpensively and how to use sensors and actuators and other kinds of controls to make sure that they operated all the time in a reliable manner.
Certainly. Well, thank you for dreaming big with us on the show, David. This is a phenomenal dream project here, and you've really shared some great stories and insights with me and our listeners today. And we are going to ask you for one last thing at the end of our conversation here, and that is advice. So when you think back over your own life and career, David, is there one piece of advice that was so helpful that you want to pass on to our listeners today?
It's really going to sound trite, but the one piece of advice that I have that stuck with me for all these years came from the scientist who was my postdoctoral advisor, Professor Irvine. And what he said to me was, never write a textbook. And I know that sounds crazy to you, that like, what kind of advice is that? But what he was thinking when he said that is, if there's something out there that other people are doing and have done, if there are things that you think maybe people expect you to do, don't do them. Do the things that you think are going to contribute to solving a big problem. Do the things that other people aren't doing, and do the things that make you happy.
And it's okay if writing a textbook makes you happy, listeners. That is the only exception, right?
Yeah, there must be a few people out there. But I think that every researcher who finds themselves at a university teaching a class is frustrated with the textbook that they have available to them. Mm-hmm. So they say, well, I could do a better job than this. And I'm sure that many of them can do a better job, but the amount of time and effort it takes to write that incrementally better textbook, for a researcher, it's probably better spending your time doing the next great piece of research or mentoring a research student and muddling along with the textbook that's available to you.
I love it. Well, David, great advice. Is there any other last piece of advice or a last note of inspiration that you want to leave us all with today?
All I could say is to your younger listeners who are thinking about a career in science and whether or not it's something for them, I think if they're someone who likes to dream and views themselves as a creative person, then a career in research is a great place to go, because the sky is literally your limit.
Well, that is a wonderful note to end on. David, if our listeners are intrigued and they want to learn more about you and the work that you do, what is the best way for them to do so or to get in touch?
Well, I am somewhat active on Twitter. My Twitter handle is @Water 4.0. It's the name of my book. So that's the Twitter handle I've been using for the last few years.
Excellent. Well, listeners, definitely follow David on Twitter. Get in touch if you have any questions. And David, it has been such a pleasure to learn more about you and the work that you do.
Thank you for having me.
And thank you for joining us. And listeners, of course, great to have you here as well. We'll see you next time on another episode of People Behind the Science.